So in this video, I'm going to go over the inverse trigonometric functions. I'll give you their derivatives, and I'll go over the integration rules that result in the inverse trigonometric functions. So overall, I'll review what the definitions are of these functions. I'll give you their domain, their ranges. I'll remind you how to evaluate them two different ways, and I'll give you the basic algebraic manipulative rules that are connected with the inverse trig functions. Afterwards, I'll go into how to find their derivatives and to give you the integrals that result in any of these six arc functions. So first, just to remind you, if a function is differentiable on an open interval and the derivative is not zero on that interval, then instantly you know that the function has an inverse and the inverse is differentiable. This is the differentiability of inverse functions rule. There's a third one also that tells you how to find the derivative, but in this case, we actually don't need to know that as we have a way to get around that particular rule. Now, in particular, the derivative of sine of x is the cosine of x, but the cosine of x on different open intervals it can be zero. And in fact, that the sine of x we know doesn't actually have an inverse function, because if you graph the sine of x, that it does not pass the horizontal line test. So what we need to do is to change the sine of x, the evaluation, in some way. The way we'll handle that is to take the sine function's domain and just not use all of it. We'll only use the portion where the input for the sine could be any angle from negative pi over 2 to pi over 2. Now in that range, you can see the blue highlighted section. You can tell that the graph is always increasing. Its derivative is positive. It's not zero. And so this sine function, this portion of it, has a inverse. I'll call this version of sine the restricted sine function. The restricted sine function has an inverse. The sine function doesn't. But we often abuse notation and just say the inverse of the sine function when we really mean the inverse of the restricted sine function. It's just cumbersome to say all that. Okay, so let's now go over the basic definition of the inverse sine, the inverse cosine, and so on. So we call them the arc sine, the arc cosine. If y equals the inverse sine of x, which we'll also call the arc sine of x, this is just a number in the angle range from negative pi over 2 to pi over 2 inclusive. So the sine of that angle, y, is x. Now this is the graph of the inverse sine. We know the graph of the inverse sine because the graph of the inverse sine and the graph of the restricted sine are mirror images in the line y equals x. From this particular picture, you automatically can tell that the domain is from negative 1 to 1 and the range is from negative pi over 2 to pi over 2 inclusive. We can also define the inverse cosine using the same kind of restriction. In this case, we'll restrict the angle range from 0 to pi, and in that angle range, the cosine does have an inverse. We'll call it the inverse cosine, or also just the arc cosine if we don't want to say the word inverse. And it's if y equals the inverse cosine of x, that means then that the cosine of y is just x. Here is the graph of the arc cosine. Again, that's just the graph of the cosine graph from 0 to pi, but reflected in the line y equals x. From this, you can tell instantly that the domain and range, in this case, the domain is from negative 1 to 1, and the range is from 0 to pi. So the secant and the tangent also have inverses, as long as you suitably restrict their angle ranges. And we'll say that their inverses are called the arc secant and the arc tangent. So if y equals the inverse secant of x, or y equals the arc secant of x, this is an angle from 0 to pi inclusive, but not including pi over 2. So that the secant of that y is x. Once again, here is the graph of the arc secant, and that is the corresponding domain and range. Notice the range is from 0 to pi. It's just that the angle can't be pi over 2. Now, there's no one who really agrees on how we should define the inverse secant. Honestly, different books define it different ways, depending upon the angle range you want to use. We use this angle range because it winds up being so that a certain algebraic rule is then true. After that, We can also see from the graph of the arc secant, though, beyond the domain range, that the arc secant has a horizontal asymptote. And in fact, if x goes and increases or decreases without bound, if x goes to infinity or negative infinity, the arc secant of x then approaches pi over 2. If y equals the arc cosecant, so the inverse cosecant of x, this is just an angle from negative pi over 2 to pi over 2, inclusive, but not including the angle of 0, so that the cosecant of that y is x. Once again, here is the graph of the cosecant, and from the graph of the cosecant, you can instantly see what the domain and the range would be. Notice the range is from negative pi over 2 to pi over 2, not including 0. And we also notice that this graph also has a single horizontal asymptote as either x were to increase or decrease without bound, that being the limit value of 0. Lastly, we have the arc tangent and the arc cotangent. Once again, if you restrict these things, the tangent and the cotangent down to a suitable range of values, those functions will have inverses. And if y equals the inverse tangent of x, the arc tangent of x, that's the angle from negative pi over 2 to pi over 2, not including the ends. So the tangent of y is x. Here, once again, is the graph of the inverse tangent, which you can get easily by looking at the corresponding graph of the tangent from negative pi over 2 to pi over 2, and then just reflecting that graph in y equals x. And from that graph, you can tell instantly what the domain and range would be. Also, you can tell that the arc tangent actually has two horizontal asymptotes. If x goes to infinity, the inverse tangent approaches pi over 2. And if x approaches negative infinity, the arc tangent approaches negative pi over 2. Similarly, you can do the exact same for the arc cotangent. It's just an angle from 0 to pi, not including the 0 or pi, so the cotangent of y is x. And that's the corresponding graph, and you get the information that you can get from that graph. That the domain, once again, is everything, and the range is from 0 to pi. And once again, the arc cotangent actually has two horizontal asymptotes. As x approaches infinity, the inverse cotangent approaches 0, and as x goes to negative infinity, the arc cotangent of x goes to pi. Good. Now, these last three slides where I'm just giving you the definitions, this is all basically coming right from trig. The only thing that's new, in fact, is the few cases here and there where I mention the limits if the function has a limit as x were to either increase or decrease without bound. It's really better just to memorize all these graphs if you can. Now that I've reviewed the basic definition of the different arc functions, let's just review how to evaluate them. So I want to know the value of the arc sine of square root of 3 over 2. You think of it as the inverse of the restricted sine of square root of 3 over 2. So there's two ways to do that. One is you just memorize a lot of stuff. And the other is you can also figure it out by using the definition of the arc functions and using the reference triangles you probably were taught in trigonometry. So if you just want to do it from memory, we recall that the sine of pi over 3 is square root of 3 over 2. And pi over 3 is in the correct angle range for an output of the arc sine. So this means then that the arc sine of square root of 3 over 2 is just pi over 3. Done. Now if you don't like that, the other way to do it is to remember that the arc sine of square root of 3 over 2 is a number. It's an angle. We'll call it y. That means that the sine of this y is a square root of 3 over 2. All I'm going to do is use the unit circle, or a circle, so that the sine of the y is, if you remember using triangles, it's the opposite over the hypotenuse. So the opposite side is square root of 3, and the hypotenuse is a length of 2. Also, I remember that the arc sine is only defined from the angle range from negative pi over 2 to pi over 2. So when I draw my circle, I'm only going to highlight quadrant 1 and quadrant 4. That's the white sections. I'll draw a triangle so that the wide length, the opposite side, is square root of 3, and the hypotenuse is 2. By using the Pythagorean theorem, you get the remaining length is 1. You can then see the triangle you formed is a 1 square root of 3, 2 triangle. That was a long time ago. That was the 30, 60, 90 triangle. So the angle that you have, I've highlighted for you, that's 60 degrees, which in radians is pi over 3. So the sine of pi over 3 is square root of 3 over 2, which means that since pi over 3 is in the correct angle range, that the arc sine of square root of 3 over 2 is pi over 3. Let's just try that again. So I want to know what's the value of the arc cosine of negative a half. So there's two ways to do it. One way is to use some information you've memorized, like the unit circle or other things, or just use the definition and use reference triangles to figure it out. From memory, the cosine of 2 pi over 3 is negative 1/2. And since 2 pi over 3 belongs to the correct angle range from 0 to pi inclusive, that means instantly that the arc cosine of negative a half is 2 pi over 3. Now, if you don't have that information memorized, you can always go by the definition and use a reference triangle. So if the arc cosine of negative a half is y, that means that y is an angle, so that the cosine of it is negative a half. Now, we recall that using right triangle trigonometry, the cosine of an angle is the adjacent side over the hypotenuse. So the adjacent side is negative 1, and the hypotenuse is 2. The hypotenuse here has to be positive for us in these problems because they always represent the distance from the point, the center of our circle, to the edge of the circle. So it's always a positive length. So that means the adjacent side is negative 1. I then remember the cosine corresponds to a change in x values. So I will draw a little circle. I will focus only on the angle range from 0 to pi. That's why I've highlighted the top portion in white. And the adjacent side of my triangle is negative 1. The opposite side of the angle that I would be using is the hypotenuse is 2, which means by the Pythagorean theorem, the opposite side would be the square root of 3. So that triangle, if you think of it in terms of absolute values, is a 1 square root of 3 two-sided triangle. We know that's a 30, 60, 90 triangle, and the angle inside the triangle is 60 degrees. Since the angle inside the triangle, adjacent to the formed by the origin, is 60 degrees, that means that that angle is pi over 3. So the angle going from the positive x-axis to the terminal point is 2 pi over 3, pi minus 2 pi over 3. So the cosine of 2 pi over 3 is negative a half. Therefore, the arc cosine of negative a half is 2 pi over 3. I think you agree that the last example was pretty intense. So it'd be nice if we had a formula that would do a lot of that work for us to evaluate these functions quickly. We really can't do that. You really need to know the picture version for a lot of it to get the basic identities and relationships down. But we can at least cut the work down for certain x values. So you should memorize this particular chart. Now myself, I memorized way back when, I memorized only this part. Well, actually up to this part right here. I memorized that much. Everything else I'm able to figure out by using identities or pictures. You were actually taught the same thing probably in trig, to memorize the sine of 0, the sine of pi over 6, the sine of pi over 4, and so on. If you didn't, you probably sat down and memorized the unit circle. It's essentially the same thing. So, but with this much and some other identities or just knowing the picture, you can easily evaluate the inverse sine and the inverse cosine or any of the arc functions for lots of nice simple values. Some of these identities that are extremely useful for the arc functions include at least these three. The arc sine of negative x is the opposite of the arc sine of x. The arc tangent of negative x is the opposite of the arc tangent of x. The arc cosecant of x is the opposite of the arc cosecant of x. These all come straight from that the corresponding graphs of those arc functions are just symmetric with respect to the origin, which means they are odd functions. And this is just the algebraic way of saying, hey, these functions are odd. Also, we get that the arc cosine plus the arc sine is pi over 2. The arc tangent plus the arc cotangent is pi over 2. And the arc secant and the arc cosecant of x is also pi over 2. These also come directly from the reference triangles, because whenever you draw one of the reference triangles, one of the angles is right next to the origin, and that's usually the arc function you're interested in. But the other acute angle is actually one of the other arc functions. So the sum of those arc functions has to be 90 degrees. This is just a way of writing that down algebraically. By putting these two together, you can also find the arc cosine of negative x to be pi minus the arc cosine of x, and so on. I myself don't memorize that one, this last category, because I can use the first two to get that one. Lastly, and the reason that we define the arc secant the way we did, the arc cosecant of x is actually the arc sine of 1 over x, and the arc secant of x is the arc cosine of 1 over x. Again, we defined the arc secant using the angle range we picked, because we could pick actually a couple of choices there. We picked the angle range we picked just so that the identity is true. Notice there's one that's missing. The arc cotangent is actually not equal to the arc tangent of 1 over x, not in general. It's true for positive values. The arc cotangent of 2, for example, is the arc tangent of 1/2. That's true. But unfortunately, the identity is not true for negative values. Let's go do some more evaluation examples. This time we'll use the identities I just gave you. For example, what if I wanted to know the arc sine of negative 1/2? Well, I know the arc sine's odd, so that's the same as the opposite of the arc sine of 1/2, and I memorized that the arc sine of 1/2 is pi over 6. So the arc sine of negative 1/2 is the opposite of pi over 6. If I want to know the arc secant of negative square root of 2, I would remember that the arc secant of x is equal to the arc cosine of 1 over x. So the arc secant of negative square root of 2 is the arc cosine of the reciprocal of the square root of 2, which is square root of 2 over 2. So now all I need to know is what is the arc cosine of negative square root of 2 over 2. Well, I know, though, that that's equal to pi minus the arc cosine of just square root of 2 over 2. But I've memorized the arc cosine of square root of 2 over 2. That's pi over 4. So the answer then is pi minus pi over 4. That's 3 pi over 4. That's me using identities. Now, you might look at it and go, well, that seems so much more difficult than just looking at a picture. Well, yeah, it is in the beginning, because you just haven't done it. But knowing the algebraic properties of the arc functions lets you do a lot more than what you could with pictures. Pictures are a good way to get you started, to give you a foundation, but you really need to know the functional equivalents of different expressions in order to do derivatives or integrations with them, or limits. So this is a good practice to get you prepared for that particular skill. Now that we've gotten past a basic review of the inverse trig functions, let's talk about the derivatives. So I'd like to know what's the derivative of the arc sine of x. I already know that the arc sine of x is differentiable, so all I need to do is use that fact. So y will then equal to the arc sine of x. That means y is a differentiable function of x. So dy dx is x. I can automatically rewrite that in an implicit form, that the sine of y then is x. You can then differentiate each side in terms of x. Well, the derivative of the sine of y, because y is differentiable, then the sine of that y is also differentiable, and I can use the chain rule to find the answer. The derivative of sine is cosine, so I have the cosine of y, and then I multiply it by the derivative of the y in terms of x. That has to equal, then, the derivative of x in terms of x, which is 1. We then just solve for dy dx. Ta-da! That's it. That's the derivative. It's just not very satisfying. It's not satisfying because y was in terms of x. So I would like the derivative of y also in terms of x. So I need to rewrite this a little bit. Well, I know what y is, though. Y is the inverse sine of x. I'll just plug that in. So that's the answer in terms of x. It's just not very, again, satisfying. The cosine of the inverse sine, I'm sure we can simplify that. So we recall that, remember, the angle range for y is only negative pi over 2 to pi over 2. So the cosine of that angle range is positive. I also remember by the Pythagorean theorem that the cosine of an angle is the square root, plus or minus, of 1 minus the sine squared of that angle. So I'll use that notationally now. I automatically know the answer must be positive. So the denominator is plus the square root of 1 minus the sine squared of the angle. The angle is the inverse sine. Well, but I'm taking the sine of the inverse sine. They just cancel, giving you x squared. So that is the derivative. The derivative of the inverse sine is actually 1 over the square root of 1 minus x squared. That's an amazing result. You start with a transcendental function and you get an algebraic one. Let's do that again. Let's look at the derivative of the arc cosine. Now this is easy because we actually have a way to write the arc cosine in terms of the arc sine if you just recall this identity, because the sum of those angles have to be pi over 2. By just taking derivatives of both sides, the derivative of the arc cosine of x is the derivative of pi over 2 minus the arc sine of x. The derivative of pi over 2 is just 0, and the derivative of the arc sine is 1 over the square root of 1 minus x squared. So we just have the extra minus in front. We then get the rule that the derivative of the arc cosine of x, the derivative of the inverse cosine, is the opposite of 1 over the square root of 1 minus x squared. Let's now discuss the derivative of the arcsecant. So the arcsecant is going to be a little interesting because of the way we defined it. We defined it to be an angle from 0 to pi inclusive, but not including pi over 2. We did that mainly because we wanted that one algebraic rule that the arcsecant of x is equal to the arc cosine of 1 over x. The cost of that is that the derivative rule now has a strange artifact in it. In particular, notice that the angle range for the arcsecant is really 2 intervals. If we ignore the endpoints, then if the input for the arcsecant is more than 1, the corresponding arcsecant of that value would be an angle from 0 to pi over 2. And if the input for the arcsecant is less than -1, the corresponding angle, arcsecant of that number, would then be an angle from pi over 2 to pi. Okay, now let's just suppose then that y equals the inverse secant of x. We already know that then this y would then be a differentiable function of x. So if y equals the inverse secant of x, then the secant of y equals x. And I can differentiate both sides in terms of x. The derivative of the secant of y in terms of x, by the chain rule, would be the derivative of secant, which is the secant of the angle y, tangent of the angle y, and then you multiply it by the derivative of that angle in terms of x, which is dy dx. That will then equal the derivative of x in terms of x, which is 1. By just solving for dy dx, that's it. That's the derivative of the inverse secant. It's just this unfortunately horrible rule. We just want to make it look nice. So to do so, I'm just going to replace everything in terms of x. Well, I know what the secant of y is. It literally is just x. And I know what y is. It's the inverse secant of x. So I can replace the denominator in that fraction with x times the tangent of the inverse secant of x. Okay, but as I did before, the tangent of the inverse secant, I can use a Pythagorean in order to go and rewrite that. We recall that the tangent of an angle is equal to plus or minus the square root of the secant squared of the angle minus 1. Thing is, we don't know if it's plus or minus. I'll just put the plus or minus in for now and worry about what happens later. So this is the same as this. Plus or minus x, just don't change the x, and replace the tangent of the angle with the square root of the secant squared of the angle minus 1. Now, part of this is really easy. This part right here is simple. Because the secant of the inverse secant of x, that's just x. So that's really just saying the square root of x squared minus 1. It's this plus or minus that's up front that I got to figure out what's going on. Okay, so let's go back to the basics. If you remember, before I did this algebra step, I had 2 different possible angle ranges. What if I was in this angle range? So y then is from 0 to pi over 2. Well, that means that this is the tangent of an angle in the first quadrant. That's positive. But for this angle range, the x is more than 1. So this x is also positive. I have a product of positive numbers. The result's positive. What if, though, I was in this angle range? In that angle range, the tangent is being taken to a tangent of an angle in the second quadrant. The tangent's negative. But for that angle range, x is less than -1. It is also negative. So once again, the denominator is a product of two numbers whose product is positive because both factors are negative. So either way, the product is positive. That's all I got to do. I have to guarantee at the end that the denominator will be positive. Well, one way to do that is to just make sure that you take this plus or minus x and you don't worry about the plus or minus. You just insist that that value there is positive. You do that by putting an absolute value on it. Because the square root of x squared minus 1, that's instantly positive. That's the definition of the square root. It's instantly positive. This way, the product of the two denominators here, the product in the denominator, is positive. We get then the final rule that the derivative of the arcsecant of x is 1 over the absolute value of x times the square root of x squared minus 1. As I've gone over the definition of all 6 inverse trig functions, and I've now gone over the derivation of the derivative of 2 of them, I won't go over the remaining 6. I'll just give you all the results. So the derivative of the arcsine of u is 1 over the square root of 1 minus u squared times the derivative of u in terms of x, assuming that the absolute value of u here is less than 1. And then the derivative of the arcsecant of u is 1 over the absolute value of u, further multiplied by the square root of u squared minus 1 times the derivative of u in terms of x. And that's if the absolute value of u is more than 1. And the derivative of the arctangent of u is 1 over u of 1 plus u squared times the derivative of u in terms of x. And because of the relationship between the arcsine and the arccosine, the arcsecant and the arccosecant, and the arctangent and the arccotangent, the derivative of the remaining inverse trig functions are just the opposites of the ones I've already given you. Let's just try this real quickly. I want to know the derivative then of these functions. So, if I want to know the derivative of f in terms of x here, I will then differentiate the inverse sine of x over 6. By the rule I gave you, that is then 1 over square root of 1 minus the u, x over 6, squared, and I multiply it by the derivative of that input. So the derivative of x over 6 is just 1/6. And that's the answer. I mean, you can't leave it that way. You got to simplify it. So there's all kinds of ways to simplify these particular expressions. It depends upon what type of algebraic manipulations you want to use. I'll just show you one sneaky trick. I'd write this as 1 over the square root of 1 minus x squared over 36. And then it's being multiplied by 1 over 6. So I'll put the 6 in the denominator, but I'll write that as the square root of 36. Because then I can write a single square root and just multiply the radicands. You would get 336 times 1, which is 36, minus x squared over 36 times 36. That's just x squared. And that's it. That's the answer. I think that's probably the easiest way to see how to simplify these things. But that's not the only way. Oh, no. There's many ways to go about doing what I just did. I just chose to show you one particular method to accomplish it. Let's try it again. So I want to know what's the derivative of this function. So then I have to differentiate in terms of x. The inverse secant of 2x to the fourth. All right, well, by the rule, that's 1 over the absolute value of 2x to the fourth times the square root of 2x to the fourth squared minus 1, further multiplied by the derivative of 2x to the fourth in terms of x, which is an 8x cubed. So this will then be equal to you would get a 8x cubed over a 2x to the fourth. So you have 8x cubed all over 2x to the fourth square root of, you get a 2x to the fourth squared. That'd be a 4x to the eighth minus 1. And then the 2 and the 8 would cancel, giving you at least a 4 in the numerator. And now you have to decide how careful you're going to be. So we have to think this through. I took the absolute value and I got rid of it, didn't I? There used to be an absolute value around the 2 and the x to the fourth. That's because it was already positive. So I didn't need the absolute value, just dropped it. So the 2 would go into 8, give me the 4. But I have to be careful to make sure it's okay. You have an x cubed divided by x to the fourth. There should be an x here. But I did just get rid of the absolute value. So at the very least, let's make sure the sign is correct. Because the x here can be positive or negative. So notice that, what if x was negative? Then that was cubed, that'd be negative. This would be to the fourth power, that'd be positive. That division would be a negative number. And then notice that this is 4 divided by, therefore, a negative number. That's still negative. That should be right then. That's the right answer. That would be the correct derivative. You just have to be careful with the absolute value when you just willy-nilly drop it to make sure that in the end you get the same algebraic expression. And usually it's safe to do what I just did, but you have to be careful with it every now and then. So that's the derivative. That's me simplifying the expression. Let's do one a little more fun. So then you are going to find then the arc functions within other functions. So you need to know how to do their derivatives. So to find this derivative, I should take the derivative of what I see. But I notice, though, it's a logarithm of a product. So I can rewrite that first as the natural log of x squared plus the natural log of the arctangent. And that can be rewritten as 2 times the natural log of x plus the natural log of the arctangent. And if you want to put this in parentheses, you can, if it makes it easier for you to see. All right, so I'll do that derivative instead. It'll be a lot cleaner. Okay, so then the derivative of 2 times the natural log of x is 2 times 1 over x plus. And the derivative of the natural log of a u is you put the u in the denominator, arctangent of x, put 1 in, and then you multiply it by the derivative of that denominator. Well, the derivative of the arctangent is 1 over 1 plus x squared. So we get the answer is 2 over x plus 1 over, and I'll choose to write it as 1 plus x squared. I'll put the polynomial first, and then follow it by the inverse trig function. And I'd leave it alone. I would not add that. I mean, you can. If you really want to write this as using a common denominator to get only one fraction, go right ahead. But honestly, I would just leave it alone. One more. I'd like to know then what's the derivative of this function. Once again, you're going to find these arc functions within other functions, and you need to know how to use them, how to find their derivative correctly using the correct product or quotient or chain rule or quotient rule, whatever. So here, the derivative would then be, I take the derivative of the outside, which is then the derivative of sine, of cosine is negative sine of the angle. I then multiply that by the derivative of the angle in terms of x. So the derivative of x minus the arc cotangent would then be the derivative of x, which is 1, minus the derivative of the arc cotangent, which is a negative 1 over a square root of 1 minus x squared. Just cleaning that up, I'd have a minus 1 plus 1 over the square root of 1 minus x squared times the sine of x minus the arc cosine of x. And that's the answer. That's the derivative. And I wouldn't bother rewriting it. That's fine. That's totally fine. Last one. Now there's many examples of how to use the derivative. I just thought I would remind you one of those. The first time we ever saw derivatives is because we were trying to find tangent lines. Let's just review that. So let's find the equation of the line tangent to this graph. To do so, I need to know then what's the derivative of y in terms of x. Notice though that y is not given to you explicitly. Y has not been solved for. I would not solve for y. What I would do is just take the derivative implicitly on both sides. So the derivative in terms of x of 3 inverse tangent of x plus inverse sine of y would then be equal to the derivative in terms of x of pi over 2. So the derivative of 3 times the inverse tangent, that'd be 3 times the derivative of inverse tangent of x in terms of x is 1 over 1 plus x squared. Plus, now I need the derivative of the inverse sine of y in terms of x. So we'll need the chain rule. That would then be 1 over the square root of 1 minus y squared. And then I multiply it by dy dx, the derivative of that y in terms of x. That would then equal the derivative of pi over 2, which unfortunately, there's still a couple students who will try using the quotient rule. That's just a constant, so that derivative is 0. Now, don't feel compelled to solve for dy dx, because we don't care. We don't care what the derivative is in general. We want to know what it is only at this point. So I would just right away, right now, just plug in x is 1 and y is the square root of 2 over 2. I'll just carry that work up here. So that would then give you a 3 times 1 over 1 plus 1 squared. Ooh, 1 squared. And then add to it 1 over the square root of 1 minus the square root of 2 over 2 squared. And I dropped the extra negative in there because I'm squaring it anyway. And that's times dy dx. And that equals 0. So this then says 3 halves, because 1 plus 1 squared is 2. You have 3 times a half, which is 3 halves. And that's plus. So the square root of 2 over 2 squared is really a half. So that's really 1 minus a half, which is a half. So now you have the square root of a half. The square root of a half reciprocated is the square root of 2. So this is the square root of 2 times dy dx, and that equals 0. So we just solve for dy dx. You get dy dx is equal to the opposite of 3 over 2 square roots of 3. 2 square roots of 2. If you want to rewrite that as negative 3 square roots of 2 over 4, that's fine. Okay, I have the slope. I have the point. The equation of the line is y minus the y coordinate of the point is equal to the slope times x minus the x coordinate of the point. That's it. That is the equation of the line tangent to the graph at that point. Now that we've gone over basic differentiation, because we have those rules, we can easily find integrations that correspond to them. All these antiderivative rules can be easily verified by just differentiating the right-hand side. I'm going to skip them all. These are all very, very useful rules. This is where a is more than 0. And notice the integration rules are not of the form of the square root of 1 minus u squared. It's a constant squared minus u squared, or u squared minus a constant squared. It's just simply more useful to write the integration rules this way. This way we don't have to do a lot of extra manipulation. So I think it'd be a good idea just to try this a few times. What if I wanted to know what this definite integral equals? Well, pretty much right away, instantly, I know the antiderivative of 1 over 1 plus x squared. That's the arctangent of x. I'm just going to evaluate it from 1 to the square root of 3. So that's the inverse tangent of square root of 3 minus the inverse tangent of 1. Notice I'm hopping between notations. I'm doing that because I'm trying to remind you that you can use either one interchangeably. I really try to use inverse tangent only when I evaluate, and I try to use arctangent any other time. This then equals the inverse tangent of square root of 3. That's pi over 3. And then we have the inverse tangent of 1, which is pi over 4. So the answer then is pi over 12. And that's it. That's that problem. Let's try the next one. I want to know the integration of this particular integrand. So it has the form, if you look at the inside, it has the form of a squared minus u squared. Because of that, I'm going to use u equals, well, if u squared is going to be 4x squared, that means u must be 2x. So then du would then be 2dx. So that dx is really a 1/2 of a du. I'll use these in here to get the integration of, well, dx is 1/2. I have a square root of 5 minus u squared du. Okay, now it's pretty easy. I just used the rule that you saw where a squared is 5. So a is actually the square root of 5. This then equals, it's of the form of 1/2 the integration of 1 over square root. If you want to put the a in so you can see it, that's a squared minus u squared du. That's fine. Really, no one writes this step, but if you want to include it, you go right ahead. That would then equal 1/2, and by the arc sine rule, that is the arc sine of u over a. But we know what u is. So the answer then is 2x over the square root of 5. If you want to rationalize the inside so there isn't a square root in the denominator, it's fine, but really, don't bother. That's that problem. Let's try it again. I want to know how to find out this particular antiderivative. This is a little more clever because this has the form of u squared minus a squared, where u is e to the x and a is 3. So it has that form of a u squared minus a squared. That's just where u squared is e to the 2x and a is 9. So I'm going to use that u actually is e to the x. That means that du would then be equal to e to the x dx. So that means that dx would then be du over e to the x, which I don't like doing that. I like having, when I substitute in, I only substitute things in if I have the old symbols in terms of the new ones entirely. So I won't use that yet until I replace the e to the x with what it's equivalent to. So dx is really du over u. Oh, I'll use this. All right, so then this has the form of the integration of dx is 1 over u du. The denominator is the square root of u squared minus 9. Just clean that up. That's the integration of 1 over a u, a square root of u squared minus 9 du. And that follows the rule of the arcsecant. Just, it doesn't have the absolute value in it. But that's okay for the integration because the absolute value gets in the final answer. So that then is equal to, it's 1 over a. A here, if a squared is 9, that means a is 3. So that's 1/3 the arcsecant of u over a, which is 3 plus c. So that's 1/3 the arcsecant of u, which is e to the x all over 3 plus c. And that's the answer to that problem. That's one way to handle it. There's many ways to write it, but essentially, you're going to be going through these steps somewhere. Let's try another one. So this time, this does not have the form of a u squared minus an a squared, or of a u squared plus an a squared, or of a squared minus u squared. These are the main forms that you see in the arc trig functions. So arcsine, arcsec, and so on. What I'm going to do then is I'm going to do a little side work first. So I notice that 6x minus x squared can be written as negative x squared plus 6x. I'm going to complete the square on that object. Now, when you complete the square, there's a kind of a process to it. You recall that if you have ax squared plus bx, if you want to complete the square, you want to add something here. The thing you add is always, you take b, you divide it by 2, you square it. But then, maybe you don't remember this one, you divide by a. That's what you should always add by. So in my case, the a in my example right here is -1, and the b here is 6. So I'll take my 6, divide by 2 to get 3. I'll square it to get 9. I'll divide by -1 to get -9. So I want to have a -9 here. But I can't just do that. I can't just say that those are equal, because they're not. One is off by -9 of the other. So if I subtract 9, I have to balance it, and I'll add 9. All right. So based upon this little fact, I get that 6x minus x squared is really negative x squared plus 6x minus 9 plus 9. That's the same as writing 9 minus the x squared plus the 6x minus the 9. That is 9 minus x squared minus 6x plus 9. And that is 9 minus x minus 3, that quantity squared. There you go. That's it. That's completing the square. Now, is there other ways to do this? Yeah, of course there are. Of course there are. This is just one way to see the process. Good. Now that we have that, the answer is going to be easy. After looking at all this side work, the integration of 1 over the square root of 6x minus x squared dx is really the integration of 1 over the square root of 9 minus x minus 3, that quantity squared, dx. And if we use the rule where u equals x minus 3 and a is 3, we notice that du is the same as dx. I'm running out of space. That then equals is not very good presentation. Not very good presentation. This is the same then as the integration of 1 over the square root of a squared minus u squared du. So that then is the arc sine of u over a. So that's x minus 3 over 3 plus c. That's the answer to the problem. It's kind of a long ways to get there, isn't it? It's a lot to do. It's because the quantity inside the square root was not a function squared plus or minus a constant squared, or a constant squared plus or minus a function squared. We had to rewrite it once. I think it's probably a good idea to do another one like that. So let's do that again. So I'm going to complete the square on what you see here. It looks to me that it has the form of a u squared plus an a squared. So let's see. 4x squared plus 4x plus 2. This is the b. This is the a. So I'll take the b and I'll divide by 2. So 4 divided by 2 is then 2. I'll square it to get 4. I'll then divide by a, which is 1. So I want to have a plus 1. Well, I'll write that then as 4x squared plus 4x plus 1. But then I'll subtract 1. But there's already a 2 there. So I have 2 minus 1. That's then plus 1. That can be written then as 2x plus 1, that quantity squared, plus 1. There you go. That's the completing the square portion. So this then equals the integration of 1 over 2x plus 1, that quantity squared, plus 1 dx. So I'll let u equal to 2x plus 1, which means that du would then be 2 times dx. So dx would then be 1/2 of du. This would then become the integration of a 1/2 du, I'll put it right here, all over u squared plus 1. That is then 1/2 the integration of 1 over u squared plus 1 du. That is 1/2 the arc tangent of u over 1, which is just u plus c. So our answer then is 1/2 the arc tangent of u, which is 2x plus 1 plus c. And that's it. That gives you a basic review of the inverse trig functions, why they're differentiable, what their derivatives would be, and how to integrate functions that give you the inverse trig functions. Notice I'm not saying to integrate the inverse trig functions themselves. That's going to be something we'll have to tackle later on. This is just those functions that when you take their antiderivatives that you get an inverse trig function.